So we were discussing about the production of rotating magnetic field. Just quickly I will summarize the results that obtained earlier. That if you have a balanced three-phase winding excited from a balanced three-phase source, then a rotating magnetic field will result. The strength of which is constant. It was some 3/2 times. The strength of this field was 3/2 times the maximum value of the individual phases. In each phase there will be n into I max, 3/2 of that. So the resultant strength of this field is 3/2 times the individual maximum value of the field produced, and the speed will be 2f by p in mechanical RPS. With respect to what? With respect to that also we should mention, with respect to this structure which houses the winding. This is important. Which houses the winding. This is the first thing. And about the direction will be decided by the phase sequence, by direction decided by the supply phase sequence. That is, this point I just tell once more. Suppose this is the windings already which is there. See, in the winding these names have been given: R1, R2, R phase winding, then Y phase winding, Y1, Y2, and then B phase winding, B1, B2. Now, if you connect the supply R phase to here, to R1, and supply Y phase to Y1, supply Y phase, and supply B phase to BS, then in which direction it will rotate? From R to Y to B in the clockwise direction. Now, if you interchange these two supply terminals, any two for that matter, for example, if you have changed this B phase to, say, here you connect, suppose instead YS, supply YS, you are connecting to B phase of the winding, which is already marked and positioned with 120 degree mutually apart, etc. There I cannot do anything. But if you change this YS to BS here, then you will see once again same strength field will be produced, but it will be rotating in the opposite direction. And number of poles, of course, will determine the mechanical speed of the rotating field. Electrical speed is F. That is there, electrical speed. Now, this is only a balanced three-phase winding. But one can show that this winding may be any balanced polyphase distributed winding. In general, I will first write what I mean to say, that any balanced, as a general case, polyphase distributed winding also produces a rotating field, when energized from a polyphase balanced supply system, supply system. So three-phase is a very special case of this, three-phase balanced. Now, of course, general proof I will not give, but what apart from three-phase, two-phase windings are also used, and which is easy to show. That I will just show that it produces also a rotating magnetic field. Are you getting? So suppose you have got a balanced two-phase supply Now you have got some idea of balanced two-phase supply by doing Scott connected transformer, etc. And suppose you have got a balanced two-phase winding distributed in space. Let us see whether it produces a rotating field or not. So for this, consider a two-phase distributed winding. Consider a two-phase distributed winding. So this I will draw like this. This is very simple, just 2 minutes it will require. Okay, and two-pole configuration, let us assume. Suppose number of poles equal to 2. I want to do a balanced two-phase winding. So two phases are there. Suppose one phase coil I put here and call it phase A, that is A1. Where should be its return for a two-pole machine? Opposite. So it will be opposite. A2 will be here. So starting of A phase, where should I start the B phase winding? 90 degree apart. In this case, mechanical, electrical degrees are same. So it will be here B1 and here B2. That's all. I mean, simplest two-phase winding one can think of. Okay. Now, obviously, this coil, A1, A2 coil, in the same line, it will produce field in the horizontal direction. So I draw this A phase coil symbolically here and tell that this is A1, A2. And B phase produces field, magnetic field, perpendicular direction. So B phase coil can be shown to be like this. B phase coil can be shown to be like this. So suppose this is B1, B2, like that. Okay. Now what you do, you have to energize this distributed balanced two-phase coil from a balanced two-phase supply. That means you join these 2 points and give supply from a balanced two-phase supply. That is, this is the neutral point of this one, such that this potential applied and this potential applied will be 90 degree out of phase. So here you give two-phase supply. And current drawn by these windings, if they are identical in nature, will be having 90 degree phase displacement. Suppose this current is drawn IA, this current is drawn IB. So let IA be is equal to some I max sin omega t, and IB is suppose lagging it by 90 degree, if I assume the supply voltage sin of omega t minus 90 degree. Okay. So once again you consider several instants of time. So for example, at omega t equal to 0, IA is 0, and IB is how much? Minus I max. And I have assumed that here I have assumed current is entering through B2. And which happens to be negative. That is actually current is entering through B1 and it is coming out. So at omega t equal to 0, what will be the field? Resultant field will be because of this and that. But A phase does not produce anything. So resultant field will be like this, only because of field. And what will be its magnitude? If I consider only the, it will be upwards, yeah, right, correct. So it will be upward direction. B phase produces like this. And what will be its magnitude? It will be that K into number of turns of B winding, how many turns are there, into I max. It will be like this. Then you can consider some other angle, say omega t. So this will have, the strength will be K into N into some I max, whatever is there. Assuming that to be only the fundamental component, let us consider sinusoidally distributed. Now, suppose you considered an instant omega t equal to 45 degrees, say, pi by 4. At that time, IA is I max by root 2, I max by root 2, and IB is minus I max by root 2, is not? Minus I max by root 2. So once again you show the direction of the current. You draw it here once again in a smaller scale. So A phase current is positive, that is it is entering through A2, so it will be cross and it will be dot here, and IB is minus 1, that is B2 is positive. So what it will be? Which one? B2 will be B2 dot this one cross. Correct? Then what you have? And both of them are having same current. So this field will be this B phase. This one. You can once again also show like this, that you can group this one here, and all these things boils down to same thing. And this one, two poles are produced like this. Similarly here, these two you can group. You see from different angles. So, and this will be like this. You can group together, and it will be like this. Anyway, resultant you can calculate. One will be upwards, like this. This one, and B phase, and A phase will be horizontal, and this will be in this direction, in this direction, and their magnitudes are same. So you can, I will not calculate this. This can be easily calculated, and it will come to same as the earlier one. So, and also as a general thing, you can, as I told you, for this case also, you can, for all instants, you can prove by considering the MMF's instantaneous values and breaking them up into x, y coordinates, taking the resultant for any arbitrary omega t. Here also you can show that the speed of this one is same as, that is 45 degree corresponding to that time has elapsed, and the field has also rotated 45 degree from A to B phase like that. That is, the field will always move from the leading to the lagging phase, like RY be there. From leading to the lagging phase it will move, the field. And the speed will be once again decided by the supply frequency and the number of poles of the machine. Okay. So it is generally, if you have a 6-phase distributed winding, you now have some feelings how to make a 6-phase distributed winding. 60 degree like that you will go. And suppose you have got a balanced 6-phase supply. If it is energized, then also it can be shown this one. How many poles it will be produced, it really does not depend upon how many phases you are doing. That depends upon how you have made your windings. Are you getting? It has nothing to do with number of phases. How many poles will be produced. Given a machine, 3-phase, 2-phase, whatever it is, you just concentrate on a single coil. See what is the coil span. Suppose you can measure it. And from that you can make it out. And how many poles it produces also you can develop. So in general, any polyphase distributed winding, that is this one, any balanced polyphase distributed winding, will produce a rotating field when energized, of course, from a balanced polyphase supply. This discovery was made by Nikola Tesla. And it was made, of course, exact timing, let me forgive, I don't remember, but the years will suffice. Around 1880s, he gave this idea. That is, if some 3-phase supply is available, then I can produce a rotating magnetic field. And from that concept, a very simple machine can be constructed. Prior to that, it was DC all along. So DC machines are much more complicated to manufacture and cost is also higher. But only impediment to this one, there was no AC supply available. Forget about 3-phase. So this discovery and paved the way. One of the reasons for going to 3-phase distributed supply was encouraged by this fact that if you have a balanced 3-phase supply, you can produce a rotating magnetic field, and from which a simple machine can be developed. This was one of the reasons, not all the reasons, but this also helped a lot to go into that. But anyway, now what I will do, I will first tell you, just because I have brought a coil. As I was telling, it is twice quite big. Anyway, this is a coil, a multi-turn coil. As you can see, these are the two turns which will be available to you. As I am telling, it goes like this. It turns like this. This is one side. It goes like this. And then it comes here, like this. And you have several turns. So this is a single coil, single multi-turn coil. And these lengths, these are the active length of the machine. And these end connections that you do at the end, these are called overhangs. And there will be no voltage induced. The length of the machine will be this one only. You getting? This one, if I draw it here, it looks like this. Rectangular coil. With several number of turns. What I mean to say, this will be the active length, where voltage will be induced. Active length of the machines. The other coppers present this side and that side are called overhang. They simply provides the connection. And your magnetic field will be perpendicular to the board and will be restricted to this zone. That is the length of the machine. Overhang will come after that. Getting? So this I just thought I will bring so that you can understand. Now my next problem will be to find out, this is important thing, to find out an expression for induced voltage, in a coil, in a, say, multi-turn coil. So the problem is like this. Suppose on the rotor of a machine you have got a single coil. You have got a single coil, multi-turn coil. So if this coil is put on the two slots, you will get several sections, but it is a single coil. And suppose this rotor I will rotate mechanically, and field has been produced by some stator windings. Okay, by some stator windings, a field has been produced. For example, the stator is having a balance, suppose 3-phase winding. You just try to understand the problem. Don't get so much involved like that. Problem is very simple. This rotor is there is a coil, rectangular coil, and suppose there is a field produced by some stator coils, which may be a distributed 3-phase coil energized. So what it will result? It will result into a rotating magnetic field. You just imagine that on the stator there is a 3-phase distributed coil and energized from 3-phase source. So with respect to stator, a rotating field is produced. And in this case, even if you don't rotate your rotor, then there will be induced voltage. See, nothing is rotating now. You get induced voltage in this coil. The field has been produced by this. Or you can generate voltage in this coil. Suppose on the stator you have got some stationary coils excited by DC current, north south, like this. You excite by DC current. A stationary field will be produced. That is, B distribution will be stationary in space. And in that case, if you want to generate voltage across this coil, across the two turns of the coil, you have to rotate it. There must be some relative velocity between these two. So what I will assume is this. Suppose somehow you have created a B distribution along the gap of the machine, which I will assume is sinusoidally distributed. That is B. This is B distribution. Flux density distribution. I have already told you how to obtain this B distribution in the air gap of a machine. So this is suppose B distribution in Weber per meter square. And this is your theta. What is theta? Theta is the space angle. And I will take electrical angle. because it may be a 4-pole machine. So theta electrical. And suppose this positive half means, suppose I attribute to this positive B to be north pole and this to be, say, south pole. This is my choice. It does not matter. So it is under north pole, it is under south pole. Once again, this will be repeated. In the developed diagram, if you develop this machine, there is a B distribution along the air gap, all along. And you have a coil. You have a coil here. So this coil has a span. This is one coil side. I am representing it by a single section. So coil. This coil span should be how much? Pi. Because electrical degree I am showing. And this coil ends, of course, these two sides are physically joined. They have to move together. It's not as it is rotated. So what I will assume is this B distribution is stationary in space, and the coil is moving from left to right with some velocity, say V meter per second, which is mechanical speed of the conductor. And I want to calculate what will be the induced voltage across the free ends of the coil, say in the free ends here. And this coil is rotated, and this is the velocity. So what is V? V is actually the tangential velocity here, V. Okay. Now how to calculate this voltage? Calculation is very simple. For example, consider this conductor. At this, as the coil is moving, suppose at any point of time it has moved, this is the instant I am considering what will be the induced voltage. So it is suppose theta. What is the value of B here? That B into length of the conductor, that is the active length of the conductor, BL into the velocity. And you can apply your right hand rule, assuming that this is actually north pole. So BLV like this, suppose the field is like this, let us assume. So BLV, it will be cross this side. And automatically this will be dot, this will be cross, like that. But what is the magnitude of this voltage? This will be B into L into V. But remember, this V is mechanical meter per second. That is what we have learned, the basics from the physics. So this will be BLV. L is the length of the machine. And remember, in 3 dimensions, suppose you look from the top, this B will be distributed all along the length of the machine. It is like a wave here. Are you getting? This is suppose this is the length of the machine, length of the conductor in 3 dimensions. It will go like this. Have you got the idea? No? This wave along the length, this B remains. So this BLV will be the induced voltage of this end, and this conductor at the back they are joined. What I mean to say. In the front, I want to see how much is the induced voltage. Similarly, in the other coil side, what will be the V? Magnitude of B will be same as this one, but only thing its polarity has reversed. So that will be also BLV magnitude. But they are added in which way? Additive way. So what will be the resultant voltage between these two? Twice BLV. That's why the other coil side should be under the, if one coil side is under the center of north pole, the other must be center of south pole. That's why coil span is pi you want to make. So twice BLV will be the instantaneous induced voltage in the conductor. Now B distribution with respect to theta, I have done it like this. So this will be 2 B max into L into V into sin theta. Obviously, theta will be a function of time as the coil is moving. This theta changes with time. And therefore, this voltage will be sinusoidally varying, harmonically varying. Okay. So this one will represent the peak value of the induced voltage in the coil. peak value of the induced voltage in the coil. That is, induced voltage maximum value is simply this one, twice V max into L into V. That theta is your omega t. What I mean by this, suppose the velocity of the coil, the velocity of the coil is suppose omega electrical radian per second. Omega electrical radian per second. Theta is this omega et. Theta is changed by this one. So that is there. So what will be the RMS value? RMS value will be root 2 divided by this by root 2. Okay. That is 1 by root 2 B max into LV. But generally, tangential velocity is not there, the rotation is there. So you try to express this V in terms of speed, RPM, etc. Anything I missed? Twice B max LV. Oh, into root. I am sorry. Yeah. You divide by root 2. Root 2 will come top. So this is there. I mean, there one can end the matter, induced voltage. But slightly you should modify it in order that in terms of RPM, etc., you can find out. What is done? Let N be the mechanical RPS of the machine. Mechanical. Then V is definitely pi dn, where d is the diameter of the rotor, dia of rotor. That is this dia. N is the mechanical RPS of the machine. So for B I can substitute this pi dn. Therefore ERMS will be root 2 B max L. If I miss anything, please point it out. Pi d n in terms of RPS of the machine. L is the length of the machine. Remember, L is the length of the conductor, active conductor, which is the length of the machine, we say, length of the machine. Now, this n RPS is the mechanical speed. Achha, now, what you do, see, still there is length and diameter in this expression. RPS is there, and length and diameters is there, and Bmax is there. So, slightly these three things are combined to represent some flux per pole. That I will now tell how this is further modified, so that the equation will come somewhat like transformer. Okay. Now, what do I mean by flux per pole? That you first try to understand. Flux per pole. This is a useful thing which is used in the expression of the induced voltage. Suppose you have got a B distribution here, sinusoidally distributed, B. This is B. This is theta electrical. So, flux per pole means under one pole, that is, this is suppose north pole, what is the total amount of flux present? So, it will basically means what? B into area is the flux. So, what is the area of this pole into, so you have to integrate because B is changing over the length. Are you getting? So, what you do, that is, suppose this is, as I told you, this is like a wave here. So, here at an angle of theta, what you consider a small element, of length here d theta. So in this small area, how much flux is entering, you try to elemental flux you find out in this area. So how much it will be? Flux density into area, this strip. How much it will be? R d theta L into R d theta is the area. But is it correct? Suppose I do R d theta is this length, okay, into L. Do you think it is really the area we understand? Why cos theta? B will take care. This is the ordinate B. This is B max sin theta. B is B max sin theta. That I will write for B. At that value, whatever B is present, into I have to multiply, remember only thing, with mechanical area. See, this theta is electrical radius. Is not flux density into mechanical area is the amount of flux crossing over that area. So this d theta, this R into d theta, this must be converted to mechanical length. This length should be mechanical. So this into electrical angle is there. So mechanical is always less. For a given electrical angle, mechanical is less. So 2 by P factor will come. So this will become, that is this elemental flux, if you call it d phi, that is whatever total flux, that is elemental area into this one. This will be twice by P into LR into B d theta. For B you substitute B max sin theta and d theta. Now everything is in electrical degree. Only thing you have to convert it to mechanical. And this should be integrated from 0 to pi. This integration is simple. If you do it, carry it out, it will be 4 by P into B max into LR. And that is, this is the phi. So this phi is called flux per pole. Flux per pole. Flux per pole. The value of which is equal to 4 by P for a P polar machine, L into R. This is very useful relationship. And its unit, of course, will be in Weber only, flux per pole. Therefore, this expression ERMS that we have got in a single coil, ERMS, which was equal to root 2, earlier we have got, into B max, some pi was also there, this one, root 2, pi, B max, then L, and for D I write 2 into R, radius, into this N. And you try to B max LR, this product you try to replace by this one, phi is equal to, so this one can be written as root 2 pi B max L into R. This product you can write it as phi into P divided by 4. Apart from that, you have got 2 here, 2 into N. Is that correct? So this will be equal to, this 2 cancels here. So this will be equal to root 2 pi into Pn by 2 into phi. This will be this thing. Induced voltage in a coil. Okay. What is N? See, in a generator, that is, it is in a generator mode. I want to generate some voltage. So, what are the two things to be inputted? The mechanical speed. So, in that term I have expressed N. And phi is the flux. Some, wherever that flux per pole is produced by energizing some coil, that current is to be controlled in order to give that. But what this Pn by 2 suggests to you, N is the mechanical speed, electrical speed of the machine, or that will be the frequency of induced voltage generated. Frequency of the induced voltage generated. So this expression is written sometimes as root 2 pi f into phi, where you should very clearly remember our input is n, not f, but we identify it with the frequency of the voltage generated in that term, or rather the rotor speed in electrical RPS. So the induced voltage, RMS value, I will write now each term root 2 pi f into phi, where f is equal to Pn by 2, and you remember n we have defined as the relative speed, because I have assumed the stator field stationary with n it is running, relative speed in mechanical RPS. So this one will be the relative speed, or the speed of the rotor rather, relative speed or speed of the rotor, whatever you write, relative speed in electrical RPS, or in hertz, that is number of revolutions per second. This happens to be the supply frequency. Okay. Is that clear? Now only thing is I have assumed is it is a single turn coil. Is not? It is a single turn coil. That is, in this diagram I have assumed a single turn coil. But suppose instead of a single turn coil, if it is a multi-turn coil and I know the number of turns, then all these things should be multiplied by n. Are you getting? Because all these EMF, coil sides EMF are all connected in series. Getting? So I will then write for a multi-turn coil, having say n number of turns, the RMS value of the induced voltage will be root 2 pi f phi into n. So this just looks like transformer induced EMF, root 2 pi f. What is the difference? There phi was phi max, and here what is phi? Phi is flux per pole. That you have to remember. Phi is the flux per pole, and f actually represents the mechanical speed of the rotor expressed in electrical. The speed of the rotor expressed in electrical. So this is the induced voltage, RMS voltage induced. Is that clear? This you should drive in your mind. In a single coil, multi-turn single coil. That is, if this coil, multi-turn coil, n number of turns is rotated in a stationary sinusoidally distributed field, the voltmeter reading here will read this one. What is this phi? Phi is the whatever B distribution is there, flux per pole, and F is Pn by 2, where n is the RPS of the machine, which can be measured with a tachometer, say, etc. This should be understood. Now the next problem is this one. Suppose we want to find out the voltage across the series combination, across the series combination of two coils, which are displaced in space by some angle. That is what I want to do. Suppose instead of a single coil, that is, you have got one coil here, multi-turn coil, one coil here, and another coil is suppose there. This is another coil. Suppose I call this coil to be coil number 1, and this coil is coil number 2. So this is one coil, 2 terminals, another coil, 2 terminals. These two I will connect in series and want to find out what is the resultant voltage, E resultant here. And suppose the coils are otherwise identical, only thing their physical positions have been displaced by some known angle, and let us assume that known angle to be some say beta electrical degree. And where is B? And suppose this rotor is rotated with n mechanical RPS, which I can measure with a tachometer, and the B is distributed by some stator coil which is stationary in space. That way I will look at it to calculate the generated voltage. So B is stationary, rotor is B distribution is stationary, and rotor just like previous problem. Only thing except two coils, now you have a single coil, you have now two coils which are displaced in space by some electrical angle beta degree. So how to find out? This is very simple, no further derivation, because if the number of turns of this coil and this coil are same, do you think individually if I connect a voltmeter here, how much it will read? Whatever it will read, do you think this voltmeter reading will be different? No, because they are undergoing same rate of change of flux. Only thing with some time lag there. So the induced voltage magnitudes across this coil and across this coil, they are same, and their magnitude will be this one, root 2 pi f phi into n, where n is the number of turns, f is the electrical speed, that is there. But then do you think the resultant voltmeter reading here, it will be 2 times? No, it will not. So what it will be? It is very simple. If you suppose this phasor represents the voltage induced in one coil, the other voltage will be say lagging this one by that angle beta, straight, by that angle beta. So resultant voltage will be only this much. Are you getting? So unlike transformer, what I am trying to tell, suppose these two coils are connected in series, and I tell R is the number, these two coils belong to some say R phase. Suppose these two coils are connected in series. I mean, one should not do like this. Dictated by transformer knowledge or things like that, that the induced voltage across this combination will be root 2 pi f into 2n, because number of turns nn into phi. This will be wrong. In case of transformer, there was nothing. Whatever is the physical number of turns, that comes there. But here it is not, although the coils are connected in series. In a single coil, the position of all the multi-turn business here, they are same. That is, we are assuming in a single coil, this will have induced voltage in same phase. That's why that N is there. For single coil it is okay, N. But once the coils are displaced, there is another coil displaced from it. This twice N thing will not come. Obviously this is less than twice V if individual voltages are V. Are you getting? So in any rotating machine, see this all the rotor peripheries are to be used. No, you should not make a generator where so much space remains unutilized. There will be large number of coils which will be distributed in space, and they will be afterwards connected in series to give you a particular, say, R phase, Y phase, B phase, like that. And you would perhaps want to know what will be the induced voltage across the combination. Are you getting? So I will continue next time, but you just try to do this one. Suppose there are 3 coils, you try to do like this. Suppose this is the angle beta. Instead of 2 coils, there may be another coil in the same way. Just try to find out, suppose there are 3 coils and the angle between the consecutive slots are, say, beta like this. Then what will be the resultant voltage? V, B, and this is also V. This is beta. So you try to find out this length in your own way. Okay, have you got, instead of 2 coils, suppose there are 3 coils. That is, the problem is there are 3 coils. This is one coil. Okay, this is suppose another coil, and there is suppose another coil here. You assume these angles are same, beta, beta. This is coil 1, 1 dashed, 1, 2, 2 dashed, like that, 2, 2 dashed, and 3, 3 dashed. And these coils, physically each one will have 2 turns available to you. Suppose you have connected them in series. Want to find out what is the resultant. Just find out an expression. So we will meet next time.